And it is my pleasure to introduce the second speaker of our inaugural session, which is Dr. Allie Nilles, who completed her PhD in computer science at the University of Illinois Urbana-Champaign in 2020, advised by Dr. Stephen M. Lavelle. She is now a postdoc in Dr. Kirsten Peterson's Collective Embodied Intelligence Lab in the Electrical and Computer Engineering Department at Cornell University. She focuses on algorithmic foundations of underactuated and otherwise weird robotic systems, and she has published in venues such as IROS, Wafer, RoboSoft, and IJRR. So take it away, Dr. Nilles.
Thank you, Professor, and thanks everyone who put this together and is joining. This is a great opportunity to get to know some people in this Robotics Institute. All right. So I'm here today to talk to you about agent-environment interactions for uncertainty reduction and communication. First of all, we're going to start with a roadmap since my background is in motion planning. So first we're going to say why. Why do we care about, especially for mobile robots, why would we want to interact with the environment? Don't we want to avoid collisions? Then I'll talk about my approach to modeling and proving robustness results for structured environmental interactions. Then I'll do a very high level overview of some cool projects and decentralized strategies that have been enabled by these kinds of agent environment interactions. And then finally, I'll end by talking about a collaboration that I'm working on now with an entomologist on environment mediated coordination and communication in granular materials. So we've got a sneak peek of the termites there. So yeah, why would we want to interact with the environment as a mobile robot? It ends up that if your body allows and you don't fall apart, or there are virtual boundaries of the environment that you can sense, this can actually reduce the resource requirements. So we just had a nice talk talking about the challenge of scalability when it comes to computation, for state estimation, and localization, but also things like hardware cost and weight, as well as communication requirements. So do you need to be in touch with a base station or not? And it ends up that the environment can actually store information. And we call this stigmergy, that's a term from biology. And we have a lot of proofs of concept of this in biological systems. So termites are able to build extremely robust, efficient mounds with no pheromones, well, they do use pheromones, but not for construction, and no central foreman, right? No, very limited sensing for each individual agent. And these kinds of interactions have also enabled robot vacuums, which are probably one of the most successful commercial robotic systems ever outside of the factory. And so I come from a background of minimalism, which is a lens kind of from computer science, which focuses on reducing the requirements of each task to find its core requirements, but it's also practical beyond theoretical investigations. It allows us to scale systems both up in number. So if we are able to easily manufacture systems like ocean drifters and CubeSats that are relatively inexpensive, it can enable a lot of research. Warehouse robots, of course, much of our logistics are currently enabled by warehouse robots that are relatively simple and also externalize a lot of their computation to the warehouse structure. And it also allows us to scale down to micro and nano robots that might not be able to fit a traditional computer or sensing resources. And so I'm particularly motivated by environmental monitoring systems in environments like forests, agriculture, freshwater, and soil science. So the current state of the art, I've got two really impressive systems here on the right from Black Swift, as well as out of Vijay Kumar's lab at the GRASP lab. And they've got a company as well called Tree Swift. So they're trying to do robust monitoring, but the problems are the current systems, of course, are very expensive per unit. They might have low fan out, so we can't control many at a time to survey a large area. They might have a low battery life. So the bottom example where they're doing SLAM only has a 30-minute battery life. And so all of our current remote sensing systems, especially in more challenging environments like freshwater environments, agricultural granular mediums, are either only able to take very sparse data or are actually done by manual collection. So people going out there with the sampling equipment. So we need a lot more scalability, especially for a lot of the environmental issues that we're facing in the future. And so my research tackles issues like this through three main themes. So first of all, we focus on challenging environments. So those might be dynamic, they might be crowded, filled with obstacles or narrow passageways. You might also be completely denied communication or localization, for example, underwater or at the micro scale. Another trend is embodied intelligence. I'm in the collective embodied intelligence lab now. This is a very broad field. There's a conference coming up in a month at that link that I encourage you all to check out. It's free to get a sense of the real breadth of this. But my focus is on really proprioceptive sensing, so sensors that are built into the robot's body, compliant actuation, minimizing the computation and exporting that to the body, as well as locally reactive strategies. And then finally, this all comes together to influence the design process for robust, scalable systems. So the design process for a system like this is much different than one for a Mars rover where the system is over-engineered. We need minimal resources per agent. We need interactive design tools for possible different settings. And we'll see different control modes. So instead of precise control of agents, we have maybe global uniform control signals or distributed control. So I'll first start out by giving an overview of how we talk about boundary interactions for simple mobile robots. So my thesis work was on two-dimensional point-based robots, so abstracting away the robot's body entirely and just saying they travel in straight lines and reorient when they reach a boundary of their environment. And we noticed just through experiments with simple controllers that there are very robust cyclic patterns. So you can see on the left, these agents are getting trapped into 2 cycles. And on the right, we're actually leveraging that property to navigate some agents through a narrow passageway. So there are several different kinds of reorientations that I considered. The first type is fixed, so zero memory, probably a totally morphological reorientation like this microorganism here on the bottom left. There's also monotonic, where you keep some memory of the direction you came from, but you still have sort of a fixed angle of departure. And we see that a lot actually in termites and other insects like that. And then there's relative, so you have no idea of the angle of the boundary that you've encountered, and you just rotate within your own plane in order to set off again. So there's lots of different kinds of reorientations that have different resource requirements is the takeaway here. And to skip a lot of details, all of this is in the paper in IJRR cited there on the bottom. We come up with a one-dimensional dynamical system that maps points on the boundary of an environment to other points. And so this might be really any kind of system, but we did linear here because that gives us some really nice composability properties. So from this dynamical system, we're actually able to compute the contraction coefficient, which is the ratio of the state space essentially that you started in to the ratio to after it's been passed through the map. So it's how much does your state space increase or decrease. So we're doing all of this in the non-deterministic case. You might start anywhere between X and Y. You're trying to bounce from the bottom of the edge up to the top. I have my laser pointer here. And you have some uncertainty delta. So there's some cone around the angle that you're trying to depart at that is uncertain. So you could bounce off at any angle here. And it ends up that this contraction coefficient is only a function of the relative angle between the 2 edges, that non-determinism delta and your intended angle theta. So we're able to efficiently compute this. And the upshot is that we can include all of this information in a roadmap if the environment is known that's aware of uncertainty, expansion, and contraction. So you can plan safe paths under uncertainty. You can also develop stronger guarantees for classes of environments that are unknown but structured. For instance, if you have a bunch of rectangles connected by straight hallways, environments like that. And then finally, in general, we can compute system performance and design constraints under this kind of strategy. So how much error is allowed for a given environment? given a certain robot with a certain amount of error, what kinds of passageways can it navigate? We can answer those kinds of questions now at a very abstract level that can be applied to many different underlying hardware systems. But in particular, I got interested in micro robotics for a while. And we became interested in, can we use this emergent dynamics to actually manipulate objects in the environment? So we put little bouncing robots in a long hallway with a box and design different strategies for them to push the box down the hallway without getting lost or ending up on the other side and working against themselves. And so this is collaborative work with some folks at Northwestern. We looked at several different designs with primitives, so sensing and actuation primitives, such as moving until you hit a wall, sensing the region you're in, these sorts of things. And then we slowly removed the primitives to show the minimal behavior that could accomplish the task. But of course, you're giving up some guarantees. And so all of my projects sort of try to explore the design space in this way. But of course, robots don't always move in straight lines. So now I'll switch gears a little bit and talk about other projects for expanding beyond this pretty harsh constraint on mobile robot motion. So one project was on Bratenberg vehicles. So if you're not familiar with Bratenberg vehicles, they are originally from synthetic psychology, sort of a thought experiment of how intelligent behavior can arise from embodied processes. So they have two sensors. Basically, they have a windshield and they can see what's on their left and what's on their right. And then those are wired directly to two actuators. So either wheels or some other propulsion mechanism. But with this framework, you can set up taxis and kinesis, which again are terms from biology. So either turning toward increasing stimulus, if you see more stimulus on the left or more on the right, turning away, speeding up, and slowing down. So with those 4 reactions, we're able to come up with 4 different modes that the system can be in. And then on top of that, we investigated different constraints on the stimulus sensing and emission. So everything from bots that have a single LED on the back and other ones that have a photodiode with a limited field of view, up to radio transmitters and receivers that are completely omnidirectional. And we analyzed the effect of those constraints. So the system looks like this, and we have the simulator on GitHub at that link. So we're switching the global mode, and then this red dot is a single controllable agent that's brighter than the others, essentially. So aggression is a nice behavior because they're turning toward and speeding up. So you're able to sort of guide the collective, even though each of these agents is extremely minimal, doesn't even know how many other agents there are, just sees there's more stimulus on my right or my left. And then there's also dispersal modes like fear, where they try to avoid stimulus. So we can imagine a lot of different tasks enabled by this kind of framework without any communication or really any onboard computation required. So this work in DARS will be coming out soon and has a lot more details on that analysis. And then this is work with a graduate student in the Collective Embodied Intelligence Lab, Stephen Surround, who I believe will be giving a more in-depth presentation later. So I won't spend too much time on this, but he designed these foam bots, which are pneumatic modules that can inflate and deflate and have interesting properties, like they have variable stiffness as they inflate, they get squishier. And they're also able to sense strain through these embedded conductive panels on their side. So there are a lot of subtle issues with these kinds of sensors, but ultimately we were able to demonstrate some consensus algorithms. I don't know if that video will play, but essentially we bent a giant sheet of these and then had them either communicate to their direct neighbors or not communicate at all and only infer from changes in their local strain what was going on around them in order to maintain consensus on strain in a giant sheet of these agents. So here the environment is really the other agents. It's the collective as the environment, and the collective dynamics and those interactions are what is providing the robustness, both in the body and in software. And then the last system I'll show you is wild bodies. So I've been working on this also with undergraduates. It's a great introductory platform. you can see them moving around here, and a comparison with the microscale particles, Janus particles on the left here. So they have a similar motion profile, zero controllability off the bat, and we are exploring different means of controlling them through either their shape, their morphology, their motility, so like their speed, momentum, and just analyzing the emergent collective dynamics. So it's a nice test bed for systems where you have the exact motion. We've gone from straight lines to totally unknown. But we might still have some properties on the system that are amenable to formalization. So properties like agents will eventually always visit all possible spaces in the environment. If you're familiar with linear temporal logic, that will raise some flags there, and you can apply those kinds of systems to these. And these could be applied to micro robots as well as agents like herding cattle, pasture rotation, being able to just guide systems of somewhat uncontrollable agents, either through structures in the environment or structures on their bodies. So some takeaways from this very high level overview of my work. When the environment is actually a large collective of coupled agents, that environment and those dynamical couplings can actually compensate for the noise and imperfections of individual agents. So that's one path to minimalism and scalability. But another really important part is the morphology and compliant reactions. So being able to execute these interactions with boundaries in their environment, whether they're physical or virtual. And finally, by abstracting this underlying physics, it enables us to really explore the design space. So with the Bradenberg vehicles, we were able to explore the effect of different sensors, actuators, and eventually we'll be able to bring more structured boundary interactions back into that project. But it's really this design space exploration that I'm targeting. So instead of trying to make the single perfect system, I want to create tools that allow us to design systems for many different complex environments and still maintain guarantees on robustness. And yeah, so I'll wrap up here with some thoughts on my current and future work. So like many of us in this environmental monitoring area, the field means a lot of different things. So we're not always in Windows XP, super smooth, homogeneous, nice field. Oftentimes it looks more like the one on the bottom where there are other agents around, the environment is heterogeneous, and you might have dangerous effects like weather and things like this. So here, robustness becomes very important. Also scalability, since these spaces, rangelands and things that we might want to monitor are vast. So we need planetary scale systems, really. There are some really interesting connections here to locomotion robophysics. So Dan Goldman and company have released a really nice review on this topic. I'll play these videos first. So the bottom one is from Dan Kodachek's lab, where they're looking at the Rex robot, and we've seen that emergent dynamics is very robust in the presence of granular materials, as well as obstacles, moving up hills, that kind of thing. And then on top, there's some work from Feifei Qian on a snake robot interacting with static obstacles on a static underlying medium. So all of these look pretty different, and they all look very different from my bouncing robots, but the similarity here is you have some sort of compliant mechanism or strategy and a rigid environment, as in the case of my bouncing robots or the snake on the top, or you have a rigid mechanism and a compliant environment if you're exploring granular mediums or aquatic environments. And it ends up that the underlying physics is very similar. And the key is really that you can use these boundary interactions to set up dynamical systems that have stability properties or limit cycles. And then even if you're not cycling in the same exact gait or sinusoidal motion every single time, you're still able to essentially use a similar method to funnel control, if people have heard of that, to stabilize the system overall, or at least narrow down the space of possibilities for the system. And yeah, there are a lot of really exciting applications in soil science, both with onboard sensors, as well as using the robot's motion and morphology itself to measure properties of the soil, the same way that we can detect a difference as we're walking. If you have your eyes closed, you can detect if you're on a new surface or not. We could imagine robots that are capable of that sort of sensing as well. So towards this goal, I'm focusing first on studying biological collectives. So this is a key point of the Collective Embodied Intelligence Lab. We really prioritize first order study of biological collectives, not just to make robotic systems better, but also just because many of the mechanisms that these systems use are totally not understood, and roboticists and technical people have a lot to contribute. So I'm working with Dr. Paul Bardunias, who's an entomologist, focuses on termites. And we are basically taking termites into the lab, sandwiching them, and then watching how they dig. And it ends up that when termites forage, they're digging through the soil, so they cannot see or sense what they're looking for before they find it, which is usually wood fallen down on the ground or buried. But it ends up that different species of termites have evolved local reactive strategies that create emergent foraging tunnels that are precisely tuned to the distribution of the food in their environment. So this is really exciting to me because it indicates there are mechanisms that exist where you can create distributed foraging patterns that are tunable to the local distribution without needing any sort of direct communication or centralized system. They also don't use pheromones during the foraging process. They only use pheromones once they find food. They'll lay down a path back to the nest. But when they're exploring, it's all tactile interactions, both between agents in the tunnel, perhaps bumping into each other, getting clogged in queues, finding little defects in the tunnel, but also single agents interacting with the environment. And it's very tied to their morphology. So on top of that, we're extending those ideas back into artificial collectives. So my goal with this platform, which I've given you a little snapshot of here, is to understand the underlying physics of this motility process through resistive granular material. So the medium is both resisting your motion, and by moving through it, you have laid down a trail that other agents can then interact with, and it will resist them less. So there are many different systems this could happen in, but it's mostly trail formation and granular materials. And there are a lot of interesting design trade-offs here that we're analyzing between agent momentum, the type of coupling between the agents, how much they're able to push and interact with each other, the resistance of the medium that they're moving through, and the difference between when they've plowed and when it's unplowed, as well as the strength of the stickmergic signal. So how high are these berms? How hard is it to break through the wall and make a new path? So the ultimate goal of this is really to abstract the underlying physics in such a way that we could implement it on many different hardware platforms, as well as unify with some of that scattering work that has been done in robophysics of locomotion. So hopefully this bird's eye view has given you a sense of how all these different projects fit into these themes and how it's all tackling some of these pressing problems that we're facing. And really how environment interactions are the key to solving all of these issues. Pretty much, unless you want a robot to just fly around and never touch anything that we want to do with robots requires interacting with the environment. So in the future, I'm hoping to bring my models of structured boundary interactions and those bouncing robots back into the analysis and design of wild body and Bradenberg systems. So able to use either a subset of agents or a strategy at boundary environments to bring some sort of order to these seemingly chaotic systems. And then, of course, continue developing design tools, integrating formal guarantees and formal methods into those tools so that it's practical, and always keeping in mind these constraints that are given to us by these tasks of environmental monitoring and these dynamic environments. So I'd like to thank, of course, our funders, everyone in the lab, Kirsten and Paul, and the organizers, and I'm happy to take any questions.
Hey, thank you. Everybody's clapping, you or me, but great talk. Question from Derek Haley. Have you looked at how collisions between agents can yield collective behavior? There's some prior work in this area, for example, the emergence of agent swarm motion and vortex formation through inelastic collisions was the title of an earlier paper.
Oh, cool. Yeah, I'm not familiar with that paper. I'll have to look that up. That sounds right up my alley. I'm familiar with the work from interagent collisions as an information source out of Georgia Tech. So there's definitely that mode as well. Currently, I'm working on dynamics of wild bodies that can shapeshift. So that's definitely an interesting avenue in terms of how do these different shapes interact with each other and what effect did those collisions have on the overall dynamics, and as well as information storage and retrieval.
So I had a question about the Brandenburg vehicle stuff. I was curious, because they're very simple, when they do, interesting things, that's amazing. In the course of your research, you've looked at a lot of different things. Have you found any thing that's the Achilles heel of the Brandenburg vehicle? Like where does it really struggle?
Great question. I think the question that's in my mind right now is resilience to agent failure or hostile agents even that are trying to take over the swarm. Since it's so reactive, how do you build in safeguards and checks to the system to be able to say, hey, there's something going wrong and our swarm is not doing what we think it should be doing. And then 3 dimensions, of course. What does this look like in 3 dimensions? There's a decent amount of formal analysis of the individual behaviors if the stimulus is stationary. But then, of course, if the stimulus is moving, it's a whole different ballgame. So we're deep into the math of that to try to figure out what are the actual constraints on when this is stable and when it's unstable.
Okay, that's very interesting. And talking about 3D things, so you showed it kind of near the end, you being inspired by the termites to dig through that. I don't know if I've seen any papers you published on that in the past, but that seems to be work in progress. It looked like a 2D digging sort of testbed apparatus that you have there. I was kind of curious more about that. And do the agents start not digging and they have to tunnel in, or are they starting at some starting position and just kind of going from there?
Well, you can see here on this slide, actually, we've got them, in 2 dimensions. Paul has done some other work on 3 dimensions, like how they respond to 3-dimensional features. They respond differently if a very resistive part of the soil is oriented straight up and down or tilted. So that's definitely an interesting direction to go. But yeah, right now we've got them in these 2D little sandwich plexiglass arenas just to see how much of this process is really due to them interacting with each other versus interacting with features of the environment.
Okay, well, thank you very much for answering my question and also direction. We're kind of running out of time right now. So I will remind everybody again that you can find these recordings of these talks are going to be on the YouTube channel for the Maryland Robotics Center. You can also link there from the website of the Maryland Robotics Center. And we have a schedule for all of the great sessions in the future that happen for the rest of this semester. And we hope to have this be an ongoing thing semester after semester. So thanks again to both of our speakers, Dr. Ho and Dr. Nilles, for being part of this inaugural session.